In this video, we're going to talk about what we call local maxima and minima. So what we've been doing throughout the course so far is getting acquainted with what the derivative is, some interpretations of that derivative, as well as learning how to take the derivative of different functions, right, using our differentiation rules. Well, now that we know about the derivative and have a good foundation in that, now we're going to use the derivative to talk about interesting aspects of functions. And so that's the topic of this next chapter that we're about to dive into. And so local maxima and minima, this section here has a lot of vocabulary and things of that nature, and then we'll get into some algebra-based work. But it says, suppose P is a point in the domain of F. So P is a point in the domain. Remember, your domain is the set of all input values where your function is defined. And so P is like an input value where your function is defined. F has a local minimum at P, so your input value P. If the function evaluated at P, the output F of P, is less than or equal to all the values of F at P near P, right? I say that very weirdly. So it says F has a local minimum at P if the functional value, the output value, the Y of the ordered pair is less than or equal to the values of F, the other Y values, the other output values of your function near P. And then the opposite occurs if we switch that less than to greater than. And so F has a local maximum at P if F of P is greater than or equal to the values of F for points that are near P. And so in this diagram right here, we have a function. This function doesn't have endpoints, and the graph doesn't have arrows here, but it's understood to be arrows, right? This function has a local max and a local min, right? The point -2, 104 is what we're going to call a local max, a local maximum, because it has a Y value that is greater than or equal to all of the Y values for all of the points that are in this area of my function, right? That's why we call it local, because it's relative to a certain area of our function. The point 8, -396 is where we're going to have a local minimum. And again, we call it local because this point is smaller than, less than, or equal to all of the points that are near it, right? And so our goal in this section is to be able to determine or find these points, whether we do so graphically or we use calculus to help us find those points. There is a note here. Local maxima and minima are also called relative maxima and minima. And sometimes people call them just local. When you put maxima and minimum together, or talk about them together as a quantity, or not a quantity, or as a thing together, you can say that that's a local or relative. They're extrema, or extreme values, right? The maximum is the most extreme value, that's the highest. The minimum is the most extreme value, that's the lowest, right? So sometimes you'll call them together local or relative extrema. All right. For all of the functions that we're going to look at, our maxima and minima that are occurring within the domain of a function that's not an endpoint, they're going to look like this. All right. And so some things that'll help us to find those things is to look at some other definitions. For instance, we call a critical point a point where f prime of p is a point p where f prime of p equals 0. F prime is your derivative, right? So a critical point is a point that makes your derivative equals 0. So it's an x value that I plug into my function and the output is 0. A critical point is also where your first derivative is undefined, all right? Those are what we're calling critical points, right? Notice it says it's a point and we're giving the x coordinates. So although we say it's a critical point, we're usually talking about the x value of that point instead of the entire point, which is an x and a y value together. When we want to talk about the y value of the critical point, we usually call that the critical value, all right? So the critical value is the value f of p at a critical point. P. So this is the y coordinate and this is the x coordinate. If you think in terms of your xy plane, x being your input variable, y being your output variable. All right. And so critical points where your derivative equals zero. We've already talked about this before, but your derivative is going to equal zero when you have a horizontal tangent line, right? Because derivative is the slope of your tangent line. Any tangent line that has a slope of zero is a horizontal line, right? And so most of the critical points that we're going to look at are going to look like this, where we have a horizontal tangent line. That's most of the critical points that we're going to look at, all right, in this course. So this is what it will look like on this function here. It looks like it's a parabola. I have a horizontal tangent line here, so I can tell that is going to be a critical point. Not all functions have critical points. For instance, this function here is completely increasing. There is never a time, even in this little area here, there's never a point where it gets to be a horizontal tangent line, right? And so this graph right here has no critical point. Okay, so critical points are going to be when your first derivative equals zero is going to be where you have a horizontal tangent line. Let's talk about the other cases where your critical points are going to occur where your function has a derivative that's undefined. All right, and so here, that's the horizontal tangent line situation I was just talking about. The undefined thing, right? At critical points where f prime of p is undefined, there is no horizontal tangent line to the graph. There is either a cusp, a corner, or an asymptote, or something else where your derivative would not be defined. And let's talk about these scenarios here, all right? Because we haven't talked about these types of functions here. Let's look at the function f of x equals x to the 2/3. All right. This function, if I graph that function, if I'm not mistaken, so I have my xy plane. This function looks like this. So your derivative is defined when your derivative from the right and your derivative from the left is exactly the same. In order for that to happen, in order for your derivative to be defined, the derivative from the left and the derivative from the right have to be equal, all right? Or the slope of the tangent line when you choose a point from the right has to be equal to the slope of your tangent line on a very, very small interval to the left. With a function that looks like this area here at x equals 0, this little area here has a sharp point. This is what we call a cusp. It's a little sharp point that our graph kind of makes. Even though it's curvy, it does still create a point. And so instead of calling it a corner, we call it a cusp because it is a rounded type scenario here. If I did the slope of my tangent line using positive 0 and a positive small value like 0.000001, and I estimated my derivative using that, I'm going to get a positive slope of my tangent line, right? And then if I do that here using negative 0.000001 and 0, a small interval around 0, and try to estimate my slope of my tangent line, I'm going to get something that's undefined. I could do the derivative of this function here. And if we try to plug in 0, we're going to see that we get something undefined. For instance, since we know how to do the derivative, I'll go ahead and do that. F prime of x is going to equal 2/3 x to the negative 1/3, right? Which is the exact same thing as 2 over 3x to the 1/3 power, right? If I were to try to plug in 0, this is where this cusp occurs, then what I would have is 2 over 3 times 0 to the 1/3, which is undefined. All right. And just so happens when we divide by 0, we can't do that mathematically. We get something that's undefined, right? This is what happens when we have a cusp. The exact same thing happens if we have a corner. One of the most popular graphs that has a corner is your absolute value function. F of x equals the absolute value of x. The absolute value function looks like this. Straight line there, straight line there. Slope of this line right here is 1. Slope of this line, or that, I guess you can call that a rate, is -1, right? It's a line. Their lines are their rays, they're half lines, right? But they meet at a corner at 0. This looks a little weird, but they make a corner. So this area here is what we're calling a corner. And so if we try to do the derivative from the left and do the derivative from the right, they would not equal each other. And so we don't have a derivative here for this function. It's undefined at x equals 0. And graphically, it appears as a corner. We may have an asymptote, right? So for instance, if we looked at the function f of x equals 1 over x, all right? This function looks something like this. All right, it doesn't look this close to the axes or whatever, but I'm trying to get you a general picture. It looks like this is my x-axis, that is my y-axis. My function is not defined at x equals 0, right? If we look at that function and we try to plug in 0 here, we're going to get 1 divided by 0, which creates what we call a vertical asymptote. And so our y-axis, or the line x equals 0, is a vertical asymptote. And so if the function has an asymptote, at an x value, then its derivative is not going to be defined because the function is not even defined. All right, and so this is the asymptote case. And there are some other cases where your derivative may not be defined, but generally it's a cusp, a corner. There's an asymptote, or your derivative is just not defined at a point, and maybe a hole or something like that. Okay, and so this is the undefined stuff. None of the functions that we're going to deal with in this chapter are going to have that undefined scenario. I'm going over this for your knowledge, right? Not all functions have a derivative at all points where the regular function is defined, right? This function here, f of x equals x to the 2/3, it's defined for any x. But if I try to plug in 0, its derivative is not defined at x equals 0. It is actually only defined at defined at other points, is only undefined at 0. All right. So you never want to forget this. The moral of this story is sometimes your derivative is not defined at certain points. All right. What we're going to focus on is this critical point stuff. I want to be able to find the maximum and the minimum values of our functions. And this is going to happen at critical points for us where our derivative is defined and equal to 0. And so let's talk about testing for local maxima and minimum. It says if a function continuous on an interval, which is its domain, has a local maximum or a minimum at P, then P is a critical point of the function or an endpoint of the interval. And so this kind of tells us or highlights where we need to go to find our local maximum and minimums, right? It's going to occur at a critical point. And if we have a closed interval, it's going to occur at the end point of that interval, right? So when I was looking at this function here, I put arrows at the end. I could have said, oh, those are not arrows, those are actually endpoints, right? So if I move these and make these an endpoint now, instead of arrows, then this is a local minimum, because it's less than, it has a y value that's less than or equal to all of the y values in this area, right? And this is a local maximum because this y value is greater than or equal to all the y values that are near it, right? And so this is what we're talking about when we say the endpoint of an interval, and that's usually for a closed interval. If it has arrows, the interval is enclosed. If it has endpoints, then of course it's closed. And so this process here we're going to use leads us to what we call the first derivative test, which is a test used to find the local maximum and minimum points that are critical points. It says, suppose P is a critical point of a continuous function f. So I have two continuous functions f here, and our critical points are going to occur where our derivative equals 0 or the derivative is undefined. So we can know here our critical point is going to be at that value there for that function, and it's going to be there for that function, right? So if I can find this critical point, and the reason why I know it's a critical point because that's where my horizontal tangent line is, right? I'm going to put this on my number line, and I'm going to put some information about my first derivative on this number line, and I know that my first derivative equals 0 at these points that I've labeled here, and I'm going to call them P here because I have a horizontal tangent line at those points, right? Horizontal tangent line. So I'm going to look at this function right here first, right? Because at this point P, we know that to the left, my function is decreasing, which means my derivative is negative. My derivative equals 0 at p because we have a horizontal tangent line, and then my function is increasing, which means my derivative is positive. Notice I labeled this f prime. And so when my derivative goes from negative, decreasing, or negative to positive, that means my function goes from decreasing to increasing. This point right here, what my graph makes is a local minimum. So f has a local minimum. So it says if f prime changes from negative sign to a positive sign, which it does here, negative sign to a positive sign, and it changes at p because p, the derivative at p was 0, then your function has a local minimum. When it changes from, okay, well, in this case, our f is increasing, which means this is my f prime line, my derivative line. F prime is positive here. I had a horizontal tangent line, so it's 0 there. We don't necessarily have to put this 0 here. In fact, I'm going to stop writing this 0 after this example here. And then my function is decreasing, so my derivative is negative. And so when the derivative is positive, the function was increasing. Derivative is negative, the function is decreasing, and it changes there. This point right here is a local maximum. So when your derivative changes from a positive sign to a negative sign, you know you have a local max. Now, remembering negative to positive or positive to negative may be hard to do because you can easily get messed up. But remember, when your derivative is negative, your function is decreasing. So I like to draw arrows from left to right going down on a decreasing interval, a negative interval for my first derivative. And then I like to go from left to right, but in the upward direction when my derivative is positive, because you can kind of see what's happening here, negative, positive. Now, we have this graph here, but when we do examples, I'm going to give you a function in its algebraic form, and you're not going to have the graph to be able to easily see, oh, negative and positive, decreasing to increasing. And so I like to put this little notation here up there. This is information about f, and these arrows here about f, whereas my number line holds information about the first derivative. There is also a second derivative test, which allows you to determine if a critical point creates a local max or a local min, but sometimes that test is inconclusive. So I'm going to skip over that test, and we're going to get to some examples where we get used to this stuff. It says below is a graph of f prime. This is the derivative that we see here. I'm looking at the derivative. We would do something totally different if I was looking at just the function, all right? So take that in mind. So I'm given the graph of the derivative. We see f prime here. That's very important. For what values of x does f, the regular function whose derivative is graphed here, has a local maximum? That's part A, and we want to know which values of x does it have a local minimum. Well, we know that for a continuous function, which is all we're going to look at in this class, the derivative is a maximum, local max or a local min is going to occur where your function has a critical point. Your critical points are where your derivative equals 0. That means the functional value, the y value of your derivative equals 0, right? So let's first graph our critical point. I'm going to create a number line. I'm going to put my critical points on that number line, right? This is my f prime number line, all right? Well, critical points are where your derivative equals 0. That means it has a 0 as a y coordinate. It's where it crosses the x-axis. So at x equals 1, I have a critical point. At x equals 3, I have a critical point. And at x equals 5, I have a critical point. Now, we know from our first derivative test, which is up here, that when my derivative changes from a negative sign to a positive sign, I'll have a local minimum for my function f. And then the opposite occurs when I have a local max, right? So I'm going to put the sign of my derivative. When I'm given the graph of my derivative, all I have to do is look at the signs of the y values, whether they're positive or negative. So for y values that are less than, x values that are less than 1, I have this part of my function that I have here in red. All those points have a positive y value, so I'm going to put a plus sign there. Then I have this, which is negative. Then this, which is positive. And then after 5, it touches 5 and then turns back and stays positive. Okay? And so what I could do here is I can do this little information about f. I know my function is increasing until I get to x equals 1, and then it has a horizontal tangent line because my derivative is 0. Then it decreases, has a horizontal tangent line at 3, It increases, has a horizontal tangent line at 5, and then it continues to increase forever, right? And so if I look at this graph, okay, and by the way, we're assuming that this stuff continues like that. Unless we see points, we assume that in this course, sorry. So I'm just gonna put it in here. Then what I know here is that my graph has a local max at x equals 1. It has a local minimum at x equals 3. And it has neither at x equals 5 because the derivative doesn't change signs. The first derivative test says it's only going to have a local min when it changes from negative to positive, and it's only going to have a local max when it changes from positive to negative. All right, it goes from increasing to a horizontal tangent line and then continues to increase. Some of you may wonder, what does that look like? It looks something like this, where there is an actual horizontal tangent line at that point where it will be like x equals 5. And so there we go. We have our function. By the way, at x equals 5, I just said there is neither a local max nor a local minimum. Now, I'm going to change this up a bit. All right. What I'm going to do now is I'm going to put some endpoints here. An endpoint here and an endpoint here. All right. That means there's an endpoint here. It's not at 0. Let me erase some things. Uh-oh, cancel. But basically, I have an endpoint here, and then I have an endpoint over here as well. All right, that's my endpoint. And this is the endpoint too, right? I am going to have either a local max or a local min at these endpoints, and we should be able to look at this to tell. Now, this is this first derivative. What I have to do is I have to look at what's going on here and incorporate what's happening to the function. If this is an endpoint, this whatever this x coordinate here, I'm going to call it A and I'm going to call that one B. At x equals A, my function has an endpoint, and then my derivative becomes positive, which means my function starts to increase. So from A, my function starts somewhere. I don't know what y value, but it increases afterwards. Well, when my function starts somewhere and it increases afterwards, we have actually a local minimum. So at x equals A, we have a local minimum. And then when I come to this B over here, my function is increasing. It has a horizontal tangent line at 5. Then it continues to increase until it gets to this x value here, B, right? And so if I increase until I get to B, then I create what we call a local minimum, a maximum. And so x equals B will be a local maximum, right? So if I were to put these endpoints on here, then x equals B, or this endpoint would be a maximum, and this endpoint over here would be a minimum. Now, remember, you're looking at this function here. I don't want you to confuse that this looks like a maximum here. You have to talk, we're answering this question about f. We're given a graph about f prime. So you can't look at that and tell about a and b. You got to kind of use this number line and this stuff here to help you figure that out. All right, it says use a calculator to find the local extrema of y equals x cubed minus 3x squared minus x. I'm going to allow you guys to do that on your own, and then we'll get together and talk about that later. Let's go to example 3 here. This is what I really want you to be able to do. It says find all critical points of the function and then use the first derivative test to determine if they are local maxima, a local minima, or neither. That should be maximum. A local maximum, a local minimum, or neither, right? So let's find our critical points first. I'm going to abbreviate that with CPs, right? To find your critical points, you take your derivative. You got to find your derivative here. The derivative of this function is 12x cubed minus 12x squared. The derivative of 6 is 0. What we need to find is what x values that we plug into that function there, our derivative function, that makes our derivative equal 0. Well, the way we do that is we set our derivatives expression equal to 0, and we solve for x. All right, to solve for x here, we can factor. Remember, when you factor polynomial expressions, the first thing you should always think about is factoring out the greatest common factor. The greatest common factor is the number and variable expression, that the largest one that goes evenly into both terms or all terms. Notice both of these terms have a 12. Both of them have an x. And when you factor using the greatest common factor, your variable expressions, you take the smallest power. The smallest power of x is squared. We take the smallest power because it has to go evenly into both of those. If I took x cubed, it wouldn't go evenly into x squared, all right? Now, factoring is the process of rewriting a sum or a difference of terms as a product of some polynomials. And so what I do is I find that greatest common factor, and I'm going to multiply that by whatever I get when I divide both of these terms by 12x squared. And you can come off to the side, right? You can say 12x cubed divided by 12x squared, where the 12s cancel, and x cubed over x squared, where two of those x's cancel, and that multiplication of 3x is there, so that just equals x. So the first term here is going to be an x. And when I factor out the 12x squared here, I'm going to have a 1 here. And so I factored this completely because I can't factor out x minus 1, but this is great, right? Because when you have a product of things, so I have 12x squared, and that's multiplied by x minus 1, and I'm saying that that equals 0. Well, the only way for things to equal 0 when you're multiplying them is for at least one of them to be 0. So we want to find all of our possible solutions, and so we set both of them equal to 0. When I divide both sides by 12, I get x squared equals 12, because 0 divided, that's a lie. X squared equals 0 because 0 divided by 12 is 0. And then I take the square root of both sides. Now, when you take the square root of both sides, I got to tell you this, because the square root is an even number, you always put on a plus or minus. So I get a plus or minus, square root of 0 is 0. Now, we know that 0 is a neutral number, so this just equals 0. But had I taken the square root of both sides and I got a number other than 0, and I didn't put that plus or minus, I would be incorrect. I would be missing one of my solutions, okay? All right, here I have x equals 1, if I add 1 to both sides. So my critical points are x equals 0 and x equals 1. Those are my candidates for my local max, my local min, or neither, right? So let's talk about extrema. What I do now is I'm going to use my first derivative test to see if I have a max or min at each of these, or neither. This is my first derivative. What I need to see if my derivative changes from positive to negative or negative to positive, right? And so what I'm going to do is I'm going to go to my derivative. This is my derivative line here, right? I'm going to go and I'm going to plug in numbers that represent these intervals here. I'm going to pick a number that's less than 0 to represent this interval. You can pick a number like -3. I'm going to pick a number between 0 and 1, like 0.5. And I'm going to pick a number bigger than 1, like 2. I'm going to plug it into my derivative. Actually, I'm going to show you how you can do it with a calculator, since this is a class that uses calculators. And so what I'm going to do here, I'm going to cut on my calculator. All right, let's go to y equals, and we're going to use our table feature of our calculator. All right, I'm going to plug in my derivative. Now, you can plug in the derivative written in factored form, which you got here, or you can plug in your derivative here. I'm going to go to the regular derivative. I'm going to put 12x raised to the third power minus 12x squared. I'm going to press enter, and then I'm going to use my table feature. All right, I'm going to go to the second window, which is here. I'm going to start at x equals -3. And I see that I want to use a half, 0.5. So what I'm going to do is I'm going to count by 0.5. So since I want to count by 0.5, I'm going to put 0.5 as my delta table, or my change for my table. I'm going to press enter, and I'm going to press auto. And then actually, let's not press auto. It doesn't matter what we put here if we don't do auto. Let's go over to ask. I'm going to press enter, so highlight ask, and I'm going to go to second table. And it's going to allow me to enter some x values so that I can see what my y values are, right? So if I plug in -3, press enter, I get a -432, right? All I care is that it's negative. I'm going to put 0.5 in there, press enter. I'm going to get a -1.5. All I care about is whether it's positive or negative. And I'm going to put 2 in there, press enter, and I get a positive, right? And so what I'm going to do is I'm going to translate that to my number line. So let's put the negative there, and the positive there. With that, this means that my function is decreasing until it gets to 0 as a horizontal tangent line. It continues to decrease some more as a horizontal tangent line. Then it goes to start to increase. So at the critical point at x equals 1, I have a local minimum. My derivative is changing from negative to positive. My function is going from decreasing to increasing. And at x equals 0, it is neither. Okay, and so this is how we can use our first derivative test to identify our local max and minimums when we know our critical points. Let's look at an additional example where we have a table of values. It says consumer demand for a product is changing over time, and the rate of change of demand f prime of t in units per week is given in week t for 0 less than or equal to t less than or equal to 10. All right, so notice here we're given the derivative. This is the derivative. Sorry about that. Can hardly see. This is the derivative. And so part A says, when is demand for the product increasing? Well, we want to know about demand. This is the derivative of demand, right? This is the derivative of demand. And so if I'm given the derivative as these values, and I want to know when this function whose derivative is given is increasing, all I have to do is look at where it's positive. So it starts being positive at t equals 3, and it's positive until 3 equals 7. So I can say from 3 to 7, all right? Or you can say between weeks 3 and 7. It says, when is demand for a product decreasing, right? So it's decreasing when the derivative is negative, right? So that's from 0 to 2, union 8 to 10, right? 0 to 2, the derivative is negative, and it's also negative from 8 to 10, right? And so I can say that, or you can write it out in words between weeks 0 and 2 and weeks 8 and 10. Okay, so either way you want to write those, that's fine. All right, it says, when is demand a local maximum? All right, well, what we're giving here is this, we know the signs of the derivative, right? The local maximums are and minima are going to occur with a derivative equals 0. Well, we don't see a 0 for any of these derivatives, right? But we do know that somewhere between weeks 2 and 3, the derivative has to be 0, right? Because before 2 and before, our derivative is negative. Then between 2 and 3, I'm just going to pick a number, any number between 2 and 3, 2.7. Or let's actually use a smaller number, let's just use the number in the middle. It doesn't matter. We don't know what type of function it is. So it may not be evenly distributed over the interval between 2 and 3. So I'm just going to pick any number between 2 and 3. 2 and 3. We know the derivative is negative at 2, and we know it's positive at 3. So somewhere between 2 and 3, the derivative becomes 0. I'm just selecting 2.5. You may select 2.6. Someone else may select 2.3. We don't know. It's just an estimate. But after that point, our derivative becomes positive because we have these positive values here. And then between 7 and 8, I'm just going to use 7.5. Our derivative becomes 0 again because after that point, our derivative is negative. And so what we can see here is that our function is decreasing, increasing, and then decreasing, right? And so when is demand at a local maximum? A local maximum here is at 7.5 weeks. All right, or at week 7.5. And when is it a minimum? It's the minimum at about week 2.5. Okay. And I'm going to say one additional thing. This is a closed interval. And so since this is a closed interval, we do have endpoints. All right. And so we have a local max and a local min on these endpoints as well. And so I know I have an endpoint at 0 and I have an endpoint at 10. Because my function, my derivative of my demand function is negative, which means my function decreases until it gets to 10. I know that I have a minimum at t equals 10. And my function is decreasing at 0, well, after 0, right? And so I know that my derivative, my function at 0, 0 is here, my function is decreasing afterwards. So I have a maximum at t equals 0. All right, and that does it for this video. We'll see you during the next one.